So, these are all words that, again, like I don't actually expect anybody to really, understand. A lot of them are even actually sort of just, sort of commercial trademarked words that Toyota uses to describe their own particular powertrain technology or whatever. But you'll see them, and so we need to make sure we understand some of those things. In a little bit more general way, what we really want to talk about is, again, we'll sort of recall the means by which we talked about hybrid electric vehicles getting some fuel economy benefit, and how do these different architectures accomplish that particular goal. Remember, we sort of talked about that. And then we'll talk about some of the trade-offs that each one that any particular architecture, any particular setup of hybrid electric vehicles is required. There's always trade-offs, and so we got to understand what those trade-offs are that they make in order to achieve fuel economy. So we talked about this again, like the characteristics of hybrid electric vehicle drivelines that can lead to efficiency, this isolation of engine, regen braking, engine downsize, electric drive mode, accessories, engine idle, energy banking, those sorts of things. We'll talk first of all about electric vehicle architectures, and then there's basically three main hybrid electric vehicle architectures, of which you saw sort of close to two out there. So EV architectures are usually very simple. I mean, there's been, sorry about that. I'll just use this. I think the one I printed has a different thing, right? Yeah, that's my bad. So global idea here is that the EV architecture looks very simple. You can think of it as it's got the electric grid that charges the battery, and then there's two-way basically power flow between the battery and the wheels. That one way is to drive the car, one way is to regenerate. It's not really there's only a couple of EVs that actually have even a very complicated transmission. The Tesla has a two-speed transmission in it, or at least I think it's the first generation Tesla had a two-speed transmission in it. Now I don't even think they have transmission. It's just one-speed transmission. But they're very simple, right? The next sort of idea is what is called a series hybrid. And it's a series hybrid in that it has what you'd sort of call a series connection between these two power flows. The power flow that is a mechanical power flow that passes, basically is a rotating shaft here, and electrical power flow. And they're connected in series, one after the other. And the global idea here is this looks a lot like an electric car, where it's got a battery, an electric motor, and all this kind of stuff like that. But the only difference is that this electric car, instead of being charged from the wall, is charged by this engine. There's not that many vehicles that are out there that are, so the nice thing is that this is a very simple idea, right? You sort of build an electric car and you put a little engine on generator on it, and you can generate power that's again like this sort of unidirectional power to charge the battery, and then the battery and the wheels operate like a conventional electric car. It's very simple, easy to conceptualize, easy to control, all those kind of nice things like that. But there's not that many vehicles that have sort of ended up using this technology, at least in production. The reasons for that, so there's a couple, we talk about a couple different kind of modes, so it's got a sort of an EV mode and, hybrid modes, a couple things. Obviously it can do regenerative braking, it can do battery charging, and it can drive while charging and doing all this kind of stuff like that. It's a very flexible mode. The benefits are, again, if we recall, the primary advantage of hybrid electric vehicles in general was to just decouple the engine from the loading on the engine from the loading that the wheels are demanding, right? And so that the series is sort of the ultimate achievement of that. You can turn off the engine, you can turn on the engine. You can operate it at more power than the car needs or less power than the car needs. It's basically completely decoupled because there's only an electrical connection between the power that's being generated by the internal combustion engine and the wheels here, right? So that's really great. So it's sort of a, we can aim for a very optimal engine operation. The other advantage here is that it looks a lot like it has the same advantages of an electric car. That, for instance, we don't have to have for instance, maybe a better way to say this is even that there's a wide speed range to electric motors, and a wide speed versus a torque versus speed range. And so you don't have to have gears, you don't have to have complicated automatic transmissions and all this kind of stuff like that. There's the idea of using, you know, a multiple motor per wheel, a multiple motor per axle that has some benefits. And like I said, the control strategies are really simple because of the degree of decoupling between the engine and motor. Does that make sense? The disadvantages here are that there's a lot of losses that are internal to the series powertrain. So, you know, if you think about the pathway between fuel energy and the wheels, in our sort of conventional car, there might be one conversion, and you know, that conversion might happen at 30% efficient or something like that, right? That's a high efficiency engine. In this case, in order for fuel energy to get to the wheels, it has to pass through all of these intermediate steps. So it's a conversion from chemical energy to mechanical energy, from mechanical energy to electrical energy, from electrical energy to chemical to electrical to mechanical and out again, right? So depending on the mode of operation you're operating in, there might be 3 to 5 different energy conversion efficiencies that kind of get tacked on to that overall, you know, what we would conventionally think about as you know, just a chemical to mechanical energy conversion, right? So the losses can be significant here. They can be, you know, oftentimes, for instance, an electric motor is 90% efficient and a battery in-out efficiency might be 80% efficient. So if you multiply 90% times 80% times 90% again, you get 64% efficiency sort of only that, you know, powertrain. And that's comparable to the, you know, 99% efficiency of a conventional transmission of a just gear set, right? So this can be a big deal. It also requires this extra components, right? A generator. And if we talk, you know, just in the same way that I think everybody can understand, if we talk about this being a cost-constrained problem, right? In this case, we have 2 of these very expensive parts, right? 2 of these parts that have maybe rare earth magnets in them or have lots of copper and have windings and all the things like that that are expensive and hard to manufacture and are not conventional vehicle components, right? So that can be a really big problem. It also has the same disadvantage as a conventional or as an electric vehicle in that the electric motor is providing all the power for the entire vehicle. So that's a big electric motor. You know, again, like if we're talking about you know, any of the cars outside, you know, we might need a 150 kilowatt, a more than 200 horsepower electric motor to drive that car at a rate that's acceptable. And then it basically, so it requires, you know, a full-size generator, a full-size electric motor, and a full-size internal combustion engine if it's not a plug-in hybrid electric vehicle, right? So it's sort of, you know, so the advantages are that you might be able to do some, you know, a large degree of decoupling between the engine and the road, but the downsides are that it might be more costly, it might be heavier, it might be all that kind of stuff. The only, so the primary example of a series vehicle that's actually in the marketplace right now, I put it in there, is a Renault Kangoo. It's like it's a small plug-in hybrid electric vehicle that's actually only built in France and only sold in Europe. But there's not that many series vehicles out here, you know, for exactly these reasons, that they can be costly. The second sort of category of hybrid electric vehicles, right, is what we call a parallel hybrid electric vehicle. And in this case, we sort of have, you know, as opposed to our series where we had all these components kind of lined up, in this case we've got them parallel, so that power can flow, you know, in this sort of parallel fashion, right? Just to explain, you know, how this goes on, we've got fuel and an engine, and this is a one-way power transmission to the wheels, of course. You can't make fuel out of engines, but then on the other hand, we've got this two-way power flow that goes along the electric motor to battery route here, all right? And so the idea is that either the vehicle could either be run by the electric motor, or driven by the electric motor, or by the engine, or both, or any combination of all those things, right? An example of a parallel hybrid is any of the Honda hybrids, so, you know, Civic or Insight are both parallel hybrids. So the parallel operation modes sort of look like this. You can have an EV mode, a pure engine mode, hybrid, regenerative braking, battery charging, any of the combinations you can think of that can pass power in those directions that we showed in that previous diagram. The advantage of the power plant, of the parallel sort of construction, is that basically we can design the capabilities of the engine and the electric motor so that they work in harmony, not that they have to work sort of with each other in series, right? So the power plants can be smaller. So for instance, if we wanted to make a engine that operated very efficiently and was significantly downsized, we could do that and then make up the extra torque or power that you would require with the electric motor. So that's sort of a strategy that requires a parallel power path in order to be able to do that. So it could be cheaper. They're more efficient, again, because we still have that direct fuel to wheel sort of connection that can be a mechanical connection and can be very efficient. The disadvantage is is that they're complex to control in general. So for instance, if you've ever driven in in any of the Honda cars or whatever, you can feel the engine turning on and turning off. You can, because there's basically a sort of a very direct connection, a mechanical connection between the engine and the wheels that wouldn't be there in a series. You also have to do some stuff like it's pretty hard to do, it's more difficult to do state of charge control, because what you end up doing is basically, instead of being able to directly charge the batteries, you have to run the engine and regen off of the same shaft, the same input shaft of the transmission. So there's some tricky stuff, but I think especially nowadays it's possible to do that, and that we can get around those things. And so you can take advantage of those efficiency advantages. Prius is a perfect example of power split hybrid. Also the Ford Escape is a power split hybrid. And we sort of have represented it pretty conceptually here, but the global idea, the only thing I sort of want you to see here is we have a parallel path, we have this, but at the same time we also have a series path, right? So if I took only this arrow and this arrow, then it would look like a parallel hybrid. And if I took this pathway here, then it would look like a series hybrid, right? It's kind of like there's both options there. And the power split device I've just represented as, you can imagine it's just a knob. And you can do it in a variety of different ways, but there's a knob there that you can send power along the parallel path, you can send power along the series path. And we could talk, if you guys want to, we can talk about the way that Prius or Escape or anything else like that does that power split. It's interesting. It's a really interesting dynamics problem. But in general... How
does the Prius do the power split?
Yeah, okay, so let's start there, huh? All right. I don't have erasers here. Let's see. So the way that the Prius does the power split is it has a planetary gear set, all right, and a planetary or epicyclic gear set. And the way that this works is, so a planetary gear set is basically a gear set that has three parts, okay? It's got this ring gear. It's got a sun gear that is in the middle here, and it's got planets. And all of these things are mounted on shafts, so that this is what's called a planet carrier. So it's just a piece of steel that carries all those planets and rotates and stuff like that. All of these, in fact, are able to spin about this center axis here. Okay. So the global idea the idea of a single gear set is that there's only 1 degree of freedom, right? If I turn this one, then this one must turn in some speed ratio that's proportional to the number of teeth in the gear and all this kind of stuff like that, right? A planetary gear set has 2 degrees of freedom. If I turned, for instance, let's just say I turned the center sun, then it could do anything that it wants to do until I, for instance, hold the outside still. And then if I turn the sun, then this thing starts to rotate around at some speed ratio that's proportional to the number of teeth on the gear and stuff like that. So it has 2 degrees of freedom. Like you can't tell it's indeterminate what it's going to do until you give it 2 inputs, and then it'll give you the 1 output. So again, in terms of, sort of like, you could think about it sort of systematically as 1 degree of freedom system. You put in 1 input and you get 1 output. And in a 2 degree of freedom system, in order to get 1 output, you have to put in 2 inputs and you can get 1 output. So it's weird to think about it that way, but it's sort of, that's the way it works. So the idea of a Prius gear set is actually what you can do is you can, by controlling 2 different speeds of that gear set, you can control the speed and torque and power of the output gear set. So I'll draw the way that it looks in the actual Prius itself. We have a internal combustion engine. We have a generator. We have a motor that's actually at the output. Okay, so the generator, I'm going to draw the same thing from the side. So the generator drives the sun gear. The engine drives the planet carrier, and then I'll draw it like this. So these are, this is a sort of a pseudo stick figure where these are the gears here. And then the motor actually basically interfaces with this, let's draw it like this. That the motor actually interfaces with the ring gear, and the ring gear interfaces with, call it the wheels here. So it's a little weird to think about, but the global idea here is that what you can do is you can, by adjusting, so then of course both motor and generator are connected electrically to a battery. And so now what we can do is we can basically look at this diagram and put connections on it that represent series and parallel paths here, all right? If you want to do a parallel path, what you want to do is you want to take the engine and drive power from the engine into this gear set right here, right? And then it will go out through this output gear set into the wheels, right? Out through the ring gear into the wheels. If you wanted to make something that was a series, it's not really a big problem to see how it works. It's a little bit hard to explain how it works, but it basically you sort of start at the same place, the planet carrier. It goes into the sun gear and can do this kind of thing again back out to the wheels. So getting that to work is a little bit tricky, but it's actually it's you could probably do the dynamics in a class that had taken differential equations or whatever. So maybe it's an AP math class or something like that. But you could do the dynamics, and it's pretty easy to see how it works. And then there's actually a lot of really good online demos. I'd urge you to look at some of those things. If you there's some. Wonder if I could even find them. There's some really cool things that talk about the way that Prius works. Power split. There's a couple of them here. Yeah, I think this is one of them. So this gives you an idea. So let's try something kind of fun. Like let's idle the car, okay? So let's watch how Prius idles. So here's all the pieces again. Sun gear is connected to the MG1, which is generator. MG2 is on the output, and engine is on the planet carrier. So what we would like to do, and the global idea is that again, we have to set 2 of these. If we set 2 of these things, then we get to. So for instance, if I set MG2 at 0 and I set the internal combustion engine at idle, 1,000 RPM, then that tells me how fast the generator has to spin. So at idle, what's happening is that this generator is going whirr, and the sun is going whirr, and this, the planet carrier that's at the ICE is going 1,000 RPM, and their speeds are matched just perfectly, so that actually the output of the wheels of the car are not doing anything. It's really pretty interesting, right? So it takes active control, and this generator actually provides that control to make it so that you can see the way that works. Again, like this planet, imagine this planet carrier here is spinning around at exactly this speed here. The generator is spinning like crazy, and the wheels are not spinning at all. So let's say, for instance, there's all sorts of, let's try to figure out how fast can a Prius drive so first of all, what I'd try to do is let's try to make the engine go as fast as it can. Here's the engine at 3,500 RPM, and I'm sort of reaching the red line of the engine, and the generator is spinning as fast as it can backwards to try to get the speed ratios to all work out right and all this kind of stuff like that. But that's how fast the car can go. Let's think, we already thought, for instance, about so let's try to make a parallel path, right? We sort of talked about a parallel path would be one where the generator is not taking any power. So if it's at zero power, everybody will remember that power is torque times speed. And so if I set speed to 0, then power also goes to 0, right? So let's set the generator speed to 0 and watch what a parallel path might look like in the Prius. I'll set the engine speed to a reasonable speed and clickety-click, something like that, right? So in that case, you can drive 50 miles an hour down the road in a Toyota Prius and do it with an entirely parallel power path. What about can we design, could we think about something that had an entirely series power path? Not on this diagram, I think. But what about how fast can the Prius go with turning the engine off in EV mode? So what happens is, we start from standstill here. We start driving the car faster and faster and faster. And what's happening is, again, we're keeping this part at 0 speed. So this interior sun gear is spinning like crazy. The planet carrier is completely still, while the ring gear is spinning the opposite direction like crazy, all to hold the engine perfectly still. And you can see that the max speed that you can go in a Prius in all EV mode is like 35, 36 miles an hour, right? So that gives you an idea what goes on there.
MG1 is the generator. Right?
Yeah, so I should label them.
Both directions counterclockwise?
Absolutely, yeah. It's an electric motor that can spin both directions, MG2.
So then that circuitry is controlled by that. There are switches to.
Mm-hmm. Yeah.
It's
so
alternating, so it doesn't matter.
Both electric motors in a Prius are permanent magnet, 4-quadrant, electric motors. So they're driven. It's got a variable. It takes in DC from the battery. It will make a variable frequency AC to control the electric motor, and it can control it in both positive and negative, in both regen and motoring.
So then
Here's
you can go that speed backwards in a Prius.
You can go that speed backwards in a Prius, just like that. Although a Prius will not let you turn on the engine and rotate the engine backwards, right?
Because you'll make gasoline.
Well, you'll do something. It'd be messy, that's for sure. So anyway, it gives you a little bit of idea of what goes on there. So now, again, like in our sort of, in our, whatever it's called, our typologies or whatever of hybrid electric vehicles, we don't necessarily say that this has to be a power split epicyclic gear train or whatever. You can do it with all sorts of other stuff. It's common to have power split with hydraulic hybrids or or anything else. I mean, you can have power electronics that'll do a power split, all this kind of stuff. The Prius is just obviously the most well-known example of that
Now,
sort of stuff.
Hyundai
Yeah.
just came out with a hybrid too. Which one do they have?
I don't know, actually. I don't know. I wish our technician was still here, right? And he'd probably know better than I do.
And
I don't
then-
know the answer to that.
The grad students downstairs were talking about a mild hybrid.
Mhm.
What does that mean?
So, again, like that's sort of a little bit of a, a soft term. But what people kind of talk about is that you can operate any of these, and I can't remember whether I actually talk about that in this one. Probably not, no. But okay, so for instance, people talk about stuff like a strong hybrid or whatever is a hybrid that has a couple of characteristics. It can drive in all electric mode, it can regenerative brake, it can idle stop, it can do all that kind of stuff like that. Things like milder hybrids or weak hybrids or whatever you want to call them are things that maybe can't do one of those things. But I sort of hesitate a little bit to like put really like hard lines in between those things just because they're not really durable hard lines. That's the sort of thing is like every automaker has their own strategy that they're tuning these things to solve, right? I mean, so for instance, not even the word hybrid is really a very good descriptor anymore. I mean, because for instance, fuels, there are fuel cell hybrids, but we don't really think of them as hybrid electric vehicles. They're actually, so for instance, a variety of U.S. automakers are going away from using the word hybrid because it's become too associated with Japanese automakers. And so they're using things that are more like eco, Malibu Eco is their particular, trademark or their branding strategy for that vehicle. They don't want to call it a hybrid because it doesn't look like a Prius and it doesn't, it's like it doesn't have a funny shape and it's not painted iridescent green. It's eco, right, which is just something different. So it's, again, like sort of, it's like being a ornithologist or something like that. You look out at the diversity of the world and you try to put everything into a box, but it doesn't always work, right? So, but but like I say, I mean, these are words that we'll hear and that your students will hear, and so it's worth understanding what they're trying to get at. But.
Back to your original diagram with the efficiency islands.
Yeah.
The Malibu with an oversized alternator doesn't actually downsize the engine and aid in.
That's right.
Support.
That's right. So they only take advantage of things that are a little bit further down that list, like for instance, idle stop, like for instance, electric accessories. That Malibu has an electric electric power steering unit and all this kind of stuff. So it's not, so why would they, but the question is, why don't they build something that's a great big power split hybrid like Prius? Because they think that their market is different. They think that their people have different price point they want to be at, different fuel economy versus price point trade-offs that a Chevy customer will make versus a Toyota customer, et cetera, right? And that's fair. They know their market, they know their customers, and so they're designing for that.
And I'm assuming this is the same setup in the Highlander and Camry now?
That's right. It's similar. Yeah, it's similar. Yeah. So, yeah, I mean, I'd just say in general, right, all those are power split hybrids. Yeah.
And they can do
No, I didn't.
They can do four-wheel drive transfer cases with.
Yeah, Highlander has a four-wheel drive.
So is that
And an
four
electric
motors?
motor in the rear diff.
So I thought that's the way it used.
Yeah.
Like I think that the new ones actually have a true
It's
T case.
It's a gear train
but yeah,
right there again.
yeah,
Yeah, they've gone. It's really an interesting system.
yeah.
So would catch me up here?
So obviously Highlander is a SUV, right? And so it's like basically almost full size SUV, and so they wanted to sell it with four-wheel drive capabilities because people are willing to pay for four-wheel drive capabilities for whatever reason. And so my understanding, and I'm a little bit rusty, was that in the original implementation, they had this power split device with a front wheel, and Highlander's also front wheel drive So it's an all-wheel drive system. It's primarily front-wheel drive, and if it detects slip, then it'll power the rear wheels as well. And so the original generation of that had a power split that looks exactly like this in the front, and an all-electric drivetrain in the rear. So an electric motor that turned the rear wheels. Now, my understanding was that in the most recent generation, whether that's post 2009 or 2010 or something like that, that they'd gone back to having a traditional transfer case for whatever reason. But it's still an all-wheel drive system. So it's got this sort of a system, but then this gears and differential would also have a transfer case going to the back with a coupling. So, okay, so you can imagine now what are the benefits? So a little bit more on the modes here. I want to get to the advantages here are that you can get a little bit of each. You can have some series, you can have some parallel operation. We sort of, when we played with that little diagram, right, you could sort of see that that the Prius and the power split can be designed so that at highway speeds or something approximating highway speeds, it'll operate in mostly parallel mode, right? That most of the power will follow this parallel path. It'll be at high efficiency, all that kind of stuff like that. But at lower speeds or in city driving or something like that, it can do this electromechanical path that's a series path. So, there's trade-offs to be had there. The disadvantages are that complexity and cost. It still has pretty big electric motors. It still has pretty big batteries. It still has pretty big engines, all that kind of stuff like that. So it's a compromise between the other two architectures. I think that's exactly the way to think about it. Now, there's a couple of different, so that's the idea of the physical way that we can put all these components together, right? Now, what about the way that they operate? There's basically sort of two different modes that these vehicles can operate in. And in general, 99% of the vehicles out there are charge-sustaining hybrid electric vehicles. Prius, our Malibu Eco out there, et cetera, et cetera. The batteries stay at about the same state of charge over the course of the day. So the car has to be charged and, so the car might discharge on at a stoplight. When the light turns green, it might have a little bit of electric mode, and the battery would discharge a little bit, and then it would charge up at the next braking event or the next time that you're driving steady state or something like that. So basically, there's no need to charge from the wall. The second mode is a charge-depleting plug-in hybrid, and that's like, for instance, the Volt or the Eco Car 2 that we're designing, where the batteries will sort of deplete over the course of a day, and it can charge from the wall. So let me just draw, let's draw a visualization of what this might look like. For instance, a conventional charge-sustaining hybrid vehicle, let's draw as a function of time. And we'll draw something here called state of charge. And state of charge, you can think about it, if you've got a glass and you're taking water out of it, it's sort of how full is the glass, right? It's not too tricky, but it goes between 0 and maybe 100% state of charge. And for a conventional hybrid, for instance, Prius or whatever, that might vary over a day's driving between 40% and maybe 60%. So you'd sort of be doing this kind of thing all day, and you drive around, and you drive up the mountain, and it might get a little bit low, and you drive down the mountain, you might get a high, and whatever, and it would just do that, right? A plug-in hybrid electric vehicle, on the other hand, you plug it in at night, it starts the day at 100% state of charge, and kind of does this kind of thing over the course of the day. You still sort of come to and from stoplights and stuff like that, but it might end up at the end of the day at 20% state of charge. And once it reaches 20% state of charge, it starts to drive like a regular old hybrid or whatever, and does its thing, right? It sort of charge sustains at 20% state of charge. That's the way a Chevy Volt works, for instance. Now, what's the benefit of doing a charge depleting hybrid is that you have two sources of energy now, gasoline and electricity. You're actually using electricity to drive the car. Now, that has some advantages, that has some costs, whatever, but it's a different way to, it's sort of halfway between an electric car and a conventional hybrid electric vehicle. got a little bit of illustrations on some ideas of the way that plug-in hybrid electric vehicles work. But this is a really interesting graph, and so it's a little probably hard to read on the screen, but you guys can pull it up. But the idea is this is a plot of the charge depleting miles that a person or that a vehicle would have. Okay, so this is called it's RCD, or a charge depleting range, and this is the daily distance. So this is the proportion of people who drive less than that distance in a day. Okay, so let's talk about an example like the Chevy Volt. Chevy Volt has about 40 miles of charge depleting range on it, right? You guys talked about that outside. You can plug it in the morning, it'll drive 40 miles, and after 40 miles, it'll start to turn on the engine. So this is a graph that's derived from statistics on how people drive, okay? So if you go to this graph, and I think I can write on this, right? Why not? I get in trouble for this all the time. I can go up here and say, look at that, like at 40 miles of range, about 60% of people drive less than 40% or than 40 miles a day. 60% of people in the United States drive less than, or 60%, it shouldn't be too scientific, but let's say 60% of people in the US drive less than 40 miles a day. So that's really great, right? I mean, that's really interesting. So so Chevy Volt, and I guarantee you that the designers at Chevrolet looked at exactly this graph, and they sort of are saying, hey, how much range should we put in our vehicle that would make it so that people can get value out of using that electricity, but not necessarily, so that they'll drive electrically and use lots of electricity instead of gas and get high fuel economy. So imagine, for instance, what would be the advantage of building a plug-in hybrid that got 10 miles of range?
Be cheaper.
Might be cheaper, exactly.
Lighter.
It'd be cheaper and lighter and everything else, right? But something like 10% of people, or maybe it's 20% of people or whatever, would drive less than 20 miles a day. So that means 80% of people or whatever, their engines are going to start, which is fine. I mean, it's sort of like, okay, it's not the end of the world, but so 80% of people, their engines are going to start, which also means that 80% of people, they're going to actually use up all the battery. Go ahead.
It might also put you in another space, though. Like when I think about that kind of range, I'm thinking of like neighborhood electric vehicles.
But yeah, so this is for a plug-in hybrid, right? So it's got an engine backup, yeah. So let's say, so for instance now, so these statistics though hold this is a survey of all of the people, it's representative of all drivers in the United States, sort of statistically or whatever, right? They actually survey several 100,000 people to get this data. Go ahead, I mean, before you...
Speculate as to why a company like Nissan or Chevy wouldn't do like I heard somebody out there say that Tesla does a so big, or so big.
Yeah.
You want small, medium, or large.
Yeah.
Because everyone's different,
Yeah, so it just costs money. It just, again, there's so for instance, the automakers already make a small, medium, large car. Like you can buy most SUVs, for instance, with a second row seat or with a third row seat, and it costs you $1,000 more to get a third row seat. And so they're doing a trade-off that says, well, we know 10% of people are going to want the third row seat, and they're willing to pay this much money for it, and they do the trade-off and understand that sort of stuff. With batteries, it's a little bit harder because if you look at the Nissan Leaf or whatever, it's a car that, it's got wheels like this, and it's got a battery that's like the whole thing underneath it. There's not that much room to put 2X or 3X or something like that inside there. And you guys saw the Volt. I mean, the Volt has a bolster in it that's 18 inches wide, full of batteries in there. I mean, it's not exactly like they had no compromises to put that battery pack in there. So they're sort of trying to figure out that trade-off. So like, for instance, now, let's say, so the Nissan Leaf, what's the ZEV range of the Nissan Leaf, an electric car, right? Like 90 miles, 80 miles, something like that. Let's say it's 80 miles. I don't know. So, for instance, we can look at the same graph and say, all right, so the Nissan Leaf drives 80 miles. What fraction of people's drive, or what fraction of people's trips is a Nissan Leaf going to satisfy? Let's go look at it, right? 80 miles, blah, blah, blah. 85, 83%. So 83% of the daily trips in the United States can be satisfied by the Nissan Leaf. That means that 17% of people are going to be dissatisfied today with their Nissan Leaf, right? I mean, 20% of people are going to say, I was trying to drive to Castle Rock and I just couldn't make it today because my Nissan Leaf wouldn't get there or whatever.
And the Leaf is just plug-in
Electric, yeah,
It
exactly.
doesn't have the backup like the Volt.
Exactly. So in that case, sort of start getting it. Yeah, that's a pretty interesting trade-off, right? I mean, so for instance, now how far do you guys drive on an average day?
I think from my house to work, it's like 5, maybe 10 miles.
Okay, good.
90 miles round trip.
You're 90 miles round trip? Yeah, so 45 there and 45 back or something like that. So for instance, you'd be on the border of a Leaf, right? Because if somebody took your EV parking place at school that one day or something like that, you might be able to limp home, but barely. So it's a good point. So anyway, I think the idea is, that plug-in hybrid electric vehicles are really nice because they get a lot of the advantages of electric cars. You can drive all electrically most of your miles, right? I mean, if you had a plug-in, if you had the Volt outside, you would never burn gas. I'm the same way. And that could be a real advantage. Plug-in hybrid electric vehicles can be really great. Electric vehicles have to battle with this, and that is that you're never going to be able to satisfy everybody's needs all the time. And so the question is, how many people are you not going to be able to satisfy? And so just in the exact same sort of anyway, it gives you a little bit of an idea of how to interpret that graph, because it's an important point, and that's there's all sorts of sort of stories about the GM executive who approved the Volt, and he looks at this graph and says, yeah, 35, 40 miles, that's just what we need. That's 50% of the drivers in the United States will never turn on their engine. Fuel economy, the equivalent fuel economy of a fleet doubles. That's what we want.
What is the cost of electricity equivalent?
Yeah, we can do that calculation. So let's say, for instance, let's have two cars that we'll use. One car will be our, and I'll rely on your calculator again too. So what we let's sort of propose two cars, two mid-sized cars. One of them is going to be our Chevy Malibu outside, and it gets the U.S. corporate average fuel economy right now is 27.5 miles per gallon. So let's just call it 28 miles per gallon. Right, and so we want to figure out, for instance, how many dollars per mile are we going to travel, right? So that's not hard to do. We're going to say gasoline is $3.50 per gallon, and we're going to do 1 over 28 miles per gallon, and that'll give us, with units of dollars per mile, some number, whatever that is. You want me to do my calculation, or are you going to do it? Okay. Sorry. So this is our gas car, right? And let's do something that is pretty close to like the Nissan Leaf, all right? And Nissan Leaf has, it's another mid-sized car. It's got 28 kilowatt hours for 100 miles. It's like, so let's say it's about, you guys will have to trust me on this number, but it's about 300 watt hours per mile. And this is, electricity is always metered in these really funny units, but perhaps you can appreciate that watt hours is a unit of energy, right? Because a watt is a joule per second, and hour is a unit of time. And so we're mixing units. It's sort of like, it's not an SI unit, but it's convenient for doing these for doing these kind of calculations, right? And then electricity, so commercial electricity, especially in Colorado, is really cheap, but let's just use a round number or something like that. And it's about 10 cents per kilowatt hour. So I'll make sure we get the units here right. And so we would have to divide by 1,000 to get 1 kilowatt hour per watt hour. So can we?
12.5 cents for the aluminum. And
3. 3 cents a kilowatt hour. It's 3 cents a mile for the electric car, right? So dollars per mile. Right? So everybody follow that calculation sort of along? Not too tricky, but just got to, again, you got to just make sure you get these the funny units of electricity metering. So, it's about 4 times less expensive. And, in Colorado, you probably pay something closer to 8 cents a kilowatt hour or whatever, but it's not too big a deal. So it'd be really nice to drive around on all. It's like buying gas for 80 cents a gallon. That'd be pretty sweet. Yeah. So, so the global idea here is okay. So the idea is, let's say you drive 2 miles a day, 1 mile a day, back and forth to work. Is an electric car or a plug-in hybrid car perfect for you? You want to say yes, right? But well, maybe, right. So even then, so let's say the problem is, if you drive 1 mile to and from work each day, you're going to save a grand total of 9 cents a day times 365 days a year is $365 or $36 a year or whatever, right? So you're going to, over 10 years, you will have saved yourself $360 by buying and driving an electric car, right? So that's not going to pay back your electric car, right? It's not going to pay back your plug-in hybrid electric vehicle, $360, right? What you need is somebody who drives exactly the range of that electric car or plug-in hybrid electric car every single day, commutes that distance every day. That way you save 45 times $360 over the lifetime of the car, which starts to sound pretty sweet now, right? I mean, whatever that is, $12,000. Now that might just buy me a Chevy Volt, right? I might just be able to save that much money over the course of the vehicle's lifetime. Does that make sense, right? So we want to think really hard about this, about the way that people drive and about the way that we can size the components of the vehicle to meet the requirements of people's driving. But the other point is that if you you have to actually drive in order to save money driving, right? It's crazy talk, but the only people who will save money driving an electric or hybrid electric car, plug-in hybrid electric car, any of those things, are people who drive. So it turns out, that there's some compromise there. You want people who drive every single day exactly the range of this, the range that your vehicle is. And those are the people who will save the most amount of money doing that, right? So anyway, it's kind of, I always think that's a really interesting trade-off, because it's sort of what it really shows is that sizing the battery pack and thinking about how far these cars should drive and thinking about how expensive they are is completely tied in to who the customer is and the way that the customer drives and values electricity and values their fuel savings. Yeah.
As we approach the end of the car's usable lifespan,
yeah,
will an industry form to recover those? Because there's some valuable metals in there, right?
There are. So right now, so Prius batteries are a nickel metal hydride chemistry, okay? And nickel metal hydride chemistry is basically a type of steel. And so those are very, very recyclable. They have not very much plastic in them. They actually have steel. They have stainless steel casings. They have this basically a nickel and a nickel type steel electrodes in them. They're very, very recyclable and very valuable. And so actually right now that's not really a problem if you go it's really easy to recycle nickel metal hydride batteries. Lithium-ion batteries are actually a little bit trickier because the technology is, and the way that you get better performance out of a lithium-ion battery, out of any the way that the world's manufacturing is going, is that we're really interested in sort of nano manufacturing, right? We're trying to make these interfaces smaller and smaller and get the electrodes closer and closer together. And so in lithium-ion batteries, literally in nickel metal hydride, you could if you sort of like can opener it off the top of a nickel metal hydride battery, you could reach your finger in and pull out a little electrode and kind of wave it around or whatever. In lithium-ion batteries, they actually tape cast them together so that they're fused, and it's almost impossible to get those separated again, right? I mean, it's sort of like if you're putting molecule A next to molecule B, next to molecule A, next to B, next to A, next to B, it's pretty hard to get them back apart again, And so recycling of lithium-ion batteries is really hard, and there is a lot of plastic that is in them and things that can't necessarily be very well recycled. So my understanding, and this is probably like 2 or 3 years old data, is that what they did to get rid of these is that you cryogenically freeze them so that they don't combust when you do this, and you put them through a shredder and put them in a landfill. And that's the end of them.
You're kidding, really?
No. So
All this
it's
difficulty in mining and other foreign countries that have the resource, and then all of a sudden we're just going to shred them.
If you open a lithium-ion battery, you have created a hazardous waste.
yeah, they're very reactive and all this kind of stuff. So it's
It's also a flammability
Yeah.
material hazard situation.
Well, because it's alkaline.
yeah, it's everything in there is very reactive. So it's very tricky. I mean, I think and part of the story, in my opinion, actually, is that this is going to be a more and more common problem. I mean, we come across it even in, it's sort of the extension of the problem where you can't get a laptop hard drive replaced anymore, right? Because you have to unglue everything to get it all taken apart and put everything back together, right? It's the same problem except for at microscopic scale that we're going to do, we're going to be mixing these materials in such a way that it's going to be really hard to recycle them. Now, there are people who are working very, very hard on trying to do lithium-ion battery recycling, and that's not to say that they won't succeed. But
I mean, you look at some cars, and you have very old cars that are the traditional internal combustion engine that
yeah,
run and work well and have gone through several owners. And we were talking, if the lifespan of a battery is 10 years and it's $50,000 or $5,000 to replace all of the batteries, or however much it is to replace the batteries, then who's going to keep their car after 8 years?
Yeah.
And if you look at loans now, loans are 7 years. So as soon as you pay off your car, I mean, you're getting a new car basically. So it's just, I mean, that.
So that's a really good point. And I'll tell you, the way that people have thought about dealing with that is what's called a second life of batteries. So for instance, the U.S. Advanced Battery Council, USABC, has some definitions of battery end of life. And what they are is that the battery can do, it's like 80% of its capacity and 80% of its peak power. And then when it hits that point, it's no longer usable in vehicles because you now have a car that instead of going 0 to 60 in 10 seconds, goes 0 to 60 in 16 seconds or something like that. It starts becoming not usable for vehicle applications. But it would be usable even at 80% capacity or 80% power for other applications like maybe battery backups for hospitals or UPSs or all sorts of things like that. So that's actually where people are spending a lot of effort. It's not, so there's certainly a lot of people, who are doing the electrochemistry and material science to try to recycle batteries. But part of the challenge as well is to actually make it so that there's a second life time for batteries that's maybe not as demanding as high cost automotive applications, but
So there's a good book called Cradle to Grave.
Mhm.
And so, I mean, if you look at that, that's great and that's really usable, but it's just one step before having it frozen and shredded. And
that's
so,
right, yeah.
Has any of the industry looked at aspects of that, of making it cradle to cradle instead of that idea of cradle to grave?
Yeah, so I think the answer is probably not as much as we should. I mean, right? I mean, the auto industry in a lot of places is actually really oriented towards improving the sustainability of some certain parts of the vehicle life cycle. Like actually now, bodies and plastics and like almost everything in a car can be recycled except for the adhesives basically now. And most of the production plants in the U.S. are all basically zero waste now. So there's lots of things that they've done that are very good steps along that pathway. Again, like it's just that the compromises that we have to make to get these batteries to work in this application are also not conducive to recycling after the fact. Now, like I say, I mean, I think the answer is if there's a value stream there, somebody will try to take advantage of it. If and you just got to leave that to R&D, to the industry, to the marketplace. But it's not a perfect solution yet. And actually, and of course, lead acid batteries are highly recyclable, and nickel metal hydride batteries are highly recyclable. And so we've had good track record to date. It remains to be seen whether we can develop that same track record for lithium.
What about some of the mechanical, like you talked about hydraulic, those just don't have the promise that electricity does?
Well, so the way to, so let's, the way to, so there's a couple things that electricity really does, or that batteries really do well, okay? We can draw a little graph. I'll show you a graph that sort of can capture some of this kind of stuff. If you want to look it up, it's actually called a Ragone plot. I'll spell it. If you just Google that, you'll find something very similar. But let's think about it for, and it's got two components here. So the first axis is watts per kilogram. The second axis, or vice versa, is watt hours per kilogram. Okay? And both of these are sort of metrics of performance for a energy storage system, right? You want to get two things out of an energy storage system. One is power, and the other is energy, right? And everything's got sort of, and usually these are on log scales, but we'll just do it sort of conceptually to make it so that I don't have to do that. But there's always trade-offs with all these things. So for instance, a conventional, let's say lithium-ion battery, like the kind of thing that would be in the Volt, is going to operate at about, let's say, on a good day, 150 watt hours per kilogram. And is going to operate at a power of about, let's say, 1,000 watts per kilogram. Okay, so this is, if I was to draw sort of a blob, let's just call this lithium ion, would look about like that. Nickel metal hydride batteries, or old technology of batteries might be something a little bit lower, nickel metal hydride might look like that. A little bit, half the energy density, half the power density, whatever. But, so for instance now, flywheels can have lots and lots and lots of power, right? You can imagine if you had a big spinning flywheel and you sort of like yank down on it, I mean, literally it would, it'd spin the room. I had my advisor used to do work on flywheel buses, and it's actually really interesting because you have to plan for failure with flywheels because they have so much momentum and so much kinetic energy in them, and it can get dissipated in a second if a bearing fails or something like that. So the problem is when you design flywheel buses, you have to be sure that when the thing fails, that it doesn't flip the bus over and do this kind of thing as the flywheels fail. It's very, one has to be very careful because the safety requirements are very demanding because the energy can be released so fast. So, for instance, like those might be something that like a flywheel has very low energy per kilogram, right? But very, very high power. So I'll put this up here, flywheels. Something like capacitors or ultracapacitors might have fractions of the energy that a battery does, but as opposed to 1,000 watt-hours per kilogram, a ultracapacitor might have something that's on the order of 30 kilowatts per kilogram, 30 times higher. Something that it would be, you could sort of think of something that would be, something that would be very high energy but not much power. Actually, fuel cells are a pretty good example of that. Fuel cells are hydrogen and oxygen. Let's say if you wanted to make a self-contained fuel cell like that often go on satellites and stuff like that, they're designed to power satellites for a long, long time. And so they can have lots and lots of energy but not much power. Another example might even actually be a nuclear reactor or something like that. Would have a lot of energy but not very much power per unit mass. They weigh a lot, they make a lot of power, but their unit mass is relatively low. So let's put over here something like fuel cells or nuclear, whatever. So the problem is everybody we would all love to have something that would operate in here, right? But the fates have conspired against us to not leave us with that chemistry or technology or anything else like that. But everybody's trying to get there. So part of the thing is that, flywheel, ultracapacitors, hydraulic hybrids sort of are up in this area here. They have lower energy, higher power, and batteries kind of occupy, what you might call kind of a sweet spot that they have the right amount of energy to power ratio. So again, like I'd urge you, these kind of plots are really cool because they explain a lot about, for instance, why do we prefer one particular technology? Why don't we use lithium-ion batteries to do starting even in Chevy Malibu or whatever out there? Well, it's because actually lead acid has much lower power energy density, but it can have higher power density. So lead acid can basically put out more power per unit mass than lithium can. At least that used to be the case, especially relative to nickel metal hydride. I should probably be careful about that. But anyway, it gives you some ideas. Okay. Anyway, so I think that's pretty much what we're going to do. So hopefully it's a little bit of discussion about what we talked about is the different types, characterizations of these hybrid cars, different ideas about the way they can operate, and what the trade-offs are that we're trying to sort of make explicit in this discussion. So the real answer is there's there's no one car for every person. There's no there's no perfect answer, right? You have to sell a particular car to a particular person and see what that and make a connection there. So.
This is a simple question that I know is complicated, but maybe you can give us a near-term answer. I think a lot of people wonder why, if you have a hybrid, that it shouldn't be a relatively straightforward thing to turn into a plug-in.
Mm-hmm.
If you could give us a couple of compelling reasons why that is a non-trivial problem.
So the sort of context for that, for instance, is that Prius has been around for for a long time, right? More than 10 years now. And it's been made as a conventional hybrid, and only this year has a plug-in hybrid Prius come out. And so why? Why was that the case? We saw actually a little bit of it in that the way that the automakers have designed, for instance, the hybrid cars that are out there, they're designing them for the same thing that they design an automatic transmission for the same thing that they design their engine controller for. It's for drivability, it's for passenger comfort, it's for fuel efficiency, it's for all these kind of things, right? And so the Prius, we just saw, for instance, it can't go over 30-something miles an hour in an EV mode. And so it sort of is a little bit of a, the power split is a little bit of a hard, it's a little bit of a hard conversion because it won't actually allow you to do that EV mode. I mean, and then then you start getting into more complicated things too. Like for instance, I mean, the electric motors in the Prius are designed, and the cooling circuits are designed for a certain drive cycle and a certain type of use. And if you get away from that, they'll overheat. I mean, and so it's always, every design is constrained by the conditions that you're putting on it. And so, I think from an engineer's perspective, I mean, right, and you guys all understand this, I think that basically, that it's a much better answer always to design from scratch for a particular application than to try to do some sort of adaptation. And so that's, I think that's always been part of the motivation for automakers to not make plug-in hybrid vehicles out of the hybrid electric vehicles that they're making. That's why you'll see, that's why Volt is a new model on a new frame, on a new electric motor, a new control strategy, a new engine, everything else. It's because if they're going to do it, they have to do it right.